Good morning. In the last class, actually, we had discussed about the Carnot cycle, the numerical and Carnot cycle, the analysis of Carnot cycle. As well, we have also seen about the Otto cycle. We had discussed about the working of Otto cycle, the basic cycle, its PVTS diagram. Also, we have seen the analysis of Otto cycle. So in this class, I'll just quickly go through the analysis of Otto cycle. Then we will see diesel cycle, and we'll also discuss some numericals on Otto and diesel cycle. I hope you are all familiar with Carnot cycle, as we have discussed it regarding the same on the last class. We have also seen how to solve numericals on Carnot cycle. Okay, so this class will be looking into Otto cycle. We'll quickly go through the analysis of Otto cycle, as you are already familiar with the same since we discussed in the last class. So Otto cycle, as you know, is invented by Nicholas Otto. It is a theoretical cycle based on which our spark ignition engine or SI engine, or commonly the petrol engine, is working. Since here heat addition and heat rejection happens at constant volume, the cycle is also known as constant volume cycle. Okay, so if you look into the PV and TS diagram, that is pressure, volume, and temperature entropy diagram, you can see that at state point 1 to state point 2, the process is a reversible adiabatic process. Okay, 1 to 2 is a reversible adiabatic process. Since reversible adiabatic is also known as isentropic, or during reversible adiabatic process entropy remains constant, the process is also known as isentropic process. Okay, and during this process 1 to 2, you can see that the pressure of the working fluid is increasing. See, the pressure is increasing and the volume is decreasing, because initial state point 1 volume was V1 and it has decreased to volume V2. So a decrease in volume and increase in pressure actually represents a compression process for a compressible fluid. Okay, since here air is the working fluid, which is compressible. Therefore, we have a reversible adiabatic or isentropic compression process happening from state point 1 to 2. Then 2 to 3 represents a constant volume process, since it is represented as a vertical line on the PV diagram. This is a constant volume process. It is a constant volume heat addition process, where an amount of heat Q in is added to the system. 3 to 4 is again a reversible adiabatic expansion process, where the pressure is decreasing and volume is increasing from 3 to 4, state point 3 to 4. And 4 to 1 is a constant volume heat rejection process, where Q out an amount of heat is rejected. Q out amount of heat is rejected from the system. Now the same process has been represented on TS diagram, temperature entropy diagram, where 1 to 2 represents reversible adiabatic or isentropic compression. Since entropy is constant, it is represented as a vertical line. And 2 to 3, and also during compression process the temperature increases, so that is evident from this process 1 to 2 marked here. Then from 2 to 3 we have constant volume heat addition process, where Q and amount of heat is added. 3 to 4 is a reversible adiabatic or isentropic expansion process, and 4 to 1 is a constant volume heat rejection process, where Q out amount of heat is rejected from the system. Now, as you know, since if you consider an engine working on Otto cycle, which is receiving an amount of heat Q in from a higher temperature source and rejecting Q out amount of heat to a lower temperature sink, then the efficiency of that engine can be represented as efficiency is equal to 1 minus heat rejected by heat supply, right? This we have already seen, 1 minus heat rejected by heat supply. So in order to analyze this cycle, or in order to find out the efficiency of the cycle, you need to know what is the amount of heat that is rejected and what is the amount of heat that is applied to the system. Since heat rejection and heat supply happens at constant volume, you can see from the PV diagram, from 2 to 3 is constant volume heat addition and 4 to 1 is constant volume heat rejection. The expression for constant volume heat addition or rejection is given as mCV delta T. mCV delta T, where M is the mass of the working fluid, CV is the specific heat at constant volume, and delta T is the temperature difference between the process. So heat supplied during the process 2 to 3 is mCV T3 minus T2, and heat rejected during the process 4 to 1 is mCV T4 minus T1. Substituting the same in the expression for efficiency, we have mCV 1 minus mCV T4 minus T1 by mCV T3 minus T2. mCV is a common term which cancels out, so we have air standard efficiency of Otto cycle is equal to 1 minus T4 minus T1 by T3 minus T2. Now The process 1 to 2 is a reversible adiabatic process. We know the temperature volume relationship for a reversible adiabatic process. The temperature volume relationship for a reversible adiabatic process um, is given by T2 minus T2 by T1 is equal to V1 by V2 raised to gamma minus 1. This is a standard relationship, temperature volume relationship for adiabatic process. Okay, we can use this relationship for adiabatic process. So T2 by T1 is equal to V1 by V2 raised to gamma minus 1. Now coming to V1 by V2. See, V1 by V2 is actually known as compression ratio. Okay, R, compression ratio R. What is V1 and what is V2, or what is compression ratio R? Compression ratio R is the ratio of total volume to clearance volume. Okay, compression ratio is the ratio of total volume by clearance volume. Now, what is total and clearance volume? We'll see the diagram that is shown here. So, in this diagram, you can see the cylinder. Now, this is the cylinder. Okay, this is the cylinder that you can see here. Inside the cylinder, you have a piston. Okay, this is the piston, which is again a cylindrical disc. So, the piston can reciprocate, that is, move to and fro inside the cylinder. And from the piston, you have a connecting rod. You can see a connecting rod over here, and this is a crankshaft shown here which rotates. So the connecting rod and the crank converts the reciprocating motion of the piston into rotary motion of the crankshaft, because piston is actually reciprocating but the crank will rotate, giving a rotary output. Now our area of concern is regarding the volumes, that is what is total volume and clearance volume. See, I have already told the piston will reciprocate. You can see the reciprocating motion shown here. The piston reciprocates inside the cylinder. The piston moves upwards until it reaches this point. Okay, this point is known as top dead center. Okay, and it stops here. It does not move further. So there will be a volume that is remaining between the top surface of the piston and the bottom surface of the cylinder, right? So that volume is known as clearance volume shown here. Okay, so when the piston reaches the top dead center, when piston moves and reaches the top dead center, a volume is remaining between the piston and the cylinder. That volume is known as clearance volume. Then the piston moves downwards and reaches the bottom dead center. Okay, so there are two dead centers. One is top dead center and another one is bottom dead center. They are called dead centers because they are the points at which the piston stops. Okay, the piston stops at the top dead center and it stops at the bottom dead center. It cannot further move away from the dead centers. Okay, in the outward directions. So when the piston reaches the bottom dead center, the volume remaining between the top surface of the piston and bottom surface of the cylinder, that is the total volume, okay, from this point to the bottom dead center, that is the total volume. Clearance volume is the volume from the bottom surface of the cylinder from here to the top surface of the piston when the piston is at top dead center. Okay, so we have clearance volume and total volume. Now the volume that is sucked by the cylinder, that is the volume between the top dead center and bottom dead center, that is the volume sucked by the cylinder. That volume is known as sucked volume. Okay, sucked volume is the sum of total volume. So total volume is the sum of clearance volume and sucked volume. I hope that is clear. So we now know what is total volume and what is clearance volume. So total volume is the volume from the cylinder, from the bottom surface of the cylinder to the top surface of the piston when the piston is at bottom dead center. Okay. So if we consider the PV diagram over here, see the total volume will be the volume from this origin point over here to the bottom dead center, that is the state point 1, because the piston will move up to this one. The piston will move from state point 2 to state point 1. This is the maximum movement of the piston. So this might be the top dead center, 2 over here. This might be the top dead center and 1 over here will be the bottom dead center, and the piston will be moving between 2 and 1. That is evident from the PV diagram because the diagram is happening in between 2 and 1. There is no volume change beyond 2 and 1. Okay, so 1 to 2, that is the region where the piston sweeps. Okay, so when the piston is at state point 1, the volume from this origin to 1, that is V1, it represents the total volume, and the piston reaches the top dead center. Okay, that's at state point 2. So the volume from origin to state point 2, that is V2, this represents the clearance volume, and the sucked volume will be V1 minus V2, right? V1 minus V2 will be sucked volume because piston will be sweeping between these 2 points. So here compression ratio R is the ratio of total volume to clearance volume. Total volume is V1 and clearance volume is V2. So V1 by V2 represents compression ratio R of the engine. That is why V1 by V2 is represented as R. Okay, so we have T2 is equal to T1 into R raised to gamma minus 1. T2 is equal to T1 into R raised to gamma minus 1. Now for again adiabatic process 3 to 4, we have 3 to 4 an adiabatic expansion process here. The temperature volume relationship is applied. So T3 by T4 is equal to V4 by V3 raised to gamma minus 1, which is equal to V4 by V3. Now V4 is equal to V1 and V3 is equal to V2. Since 2 to 3 and 4 to 1 are constant volume process, you can write it as V1 by V2 raised to gamma minus 1. Now V1 by V2 is the ratio of total volume by clearance volume, that is compression ratio R. So it is R raised to gamma minus 1. Hence T3 is equal to T4 and R raised to gamma minus 1. Okay. So we got an expression for T3 in terms of T4 and T2 in terms of T1. Okay. So T3 in terms of T4 and T2 in terms of T1. So you can substitute in this expression. Okay. Instead of T2, you can substitute as T1 into R raised to gamma minus 1. T1 into R raised to gamma minus 1. And instead of T3, you can substitute T4 into R raised to gamma minus 1. Okay, T3 is T4 into R raised to gamma minus 1. Substituting the same. And R raised to gamma minus 1 is a common term. So taking R raised to gamma minus 1 outwards, you have T4 minus T1 and T4 minus T1 in numerator and denominator. Cancel that and you will get efficiency of Otto cycle is equal to 1 minus 1 by R raised to gamma minus 1. Okay. So air standard efficiency of an Otto cycle is given by 1 minus 1 by R raised to gamma minus 1, where R is the compression ratio and gamma is the index of adiabatic expansion. For air, the value of gamma is 1.4. Okay. So I hope the analysis of Otto cycle is clear. Now we'll quickly see a problem on. We have already discussed this problem on Carnot cycle. Okay, I hope this problem is clear. This is very simple problem on Carnot cycle. Direct use of expression. We have already discussed this in the last class. And then we have also seen this problem regarding Carnot cycle. We have also seen this problem. Okay. So you may just go through the problem once again and see how it is. We have already seen this. Okay, this is the solution for the Carnot cycle problem. Now next is a numerical on Otto cycle. So here the efficiency of an Otto cycle is given as 45%. Efficiency of an Otto cycle is given as 45%. And the gamma is the index of adiabatic expansion. Gamma is given as 1.5. You need to find its compression ratio. Okay. So the given quantities are efficiency is given as efficiency of Otto cycle is given as 45%, and gamma is given in the question as 1.5. You need to find out compression ratio R. So since it is an Otto cycle, we already know we have right now seen the expression for efficiency of Otto cycle. So the expression for efficiency is efficiency of Otto cycle is equal to 1 minus 1 by R raised to gamma minus 1. Right, 1 minus 1 by R raised to gamma minus 1. So we'll quickly look into the expression over here. Expression is 1 minus 1 by R raised to gamma minus 1. Okay. So efficiency is given in the question, it is 45%. So 0.45 is equal to 1 minus 1 by, you need to find out R. Gamma is given as 1.5. Only R is the unknown in the equation. Okay. Gamma is given as 1.5 and efficiency is 45%, 0.45. So substituting, you will get the value of R, where R is compression ratio. So that is a simple question. You can solve the question. Okay, you can solve and find the value of R. Fine. I hope that is a simple question. You can solve it. Next, we will move on to another problem on Otto cycle, another numerical on Otto cycle. So here, in an Otto cycle, condition of air is 27 degrees Celsius and 1 bar at the start of compression. Okay. If the clearance volume is 20% of the sucked volume, estimate temperature at the end of compression and air standard efficiency of the cycle. Fine. So since in the question the cycle is given as Otto cycle, the best way to solve the problem is always draw the PV and TS diagram. Once you identify the cycle, first thing is you identify the cycle and then you draw the PV and TS diagram of the cycle. Okay. So since it is an Otto cycle, we can draw the PV, pressure, volume and temperature entropy chart of the cycle. So it is a constant volume cycle. It has 4 processes. One is reversible adiabatic compression, constant volume heat addition. Third one, reversible adiabatic expansion. Fourth one, constant volume heat rejection. So the same has been marked on PV and TS diagram. Now, in an Otto cycle, the condition of air is 27 degrees Celsius and 1 bar at the start of compression. So, compression process, reversible adiabatic compression, is happening from 1 to 2. So, the start of the compression represents state point 1. At state point 1, the temperature T1 is 27 degrees Celsius and pressure P1 is 1 bar. And so you can write that given quantity. That is the third step in solving the problem. The first step is you identify the cycle. Second step is draw the PV and TS diagram. Third step is write the given conditions in standard units. Okay, write the given conditions in standard units. So the given condition is temperature T1 is 27 degrees Celsius. So plus 273, that is 300 Kelvin. Kelvin is the standard unit of temperature. Then pressure is given as 1 bar. So 1 bar is 1 into 10 raised to 5 Newton per meter square. Newton per meter square is the standard unit of pressure. Okay. Now, if the clearance volume is 20 percentage of sept volume, the clearance volume is given as 20% of sept volume. So you have to know what is clearance volume. We know that total volume is V1, right? From origin to state point 1. V1 represents total volume, and the piston moves from 1 to 2. Okay, so 2 is the top dead center and 1 is the bottom dead center, or 2 is the inner dead center and 1 is the outer dead center. Okay, it can be, you can either represent it for a vertical engine. Okay, so this figure shown here, this is a vertical engine. For this vertical engine, the top dead center, the topmost portion up to which the piston moves, is known as top dead center, and the bottommost portion is known as bottom dead center. Now, if this was a horizontal engine, okay, instead of this vertical engine, this can be a horizontal engine. If it is an horizontal engine, then instead of top dead center, we will say it as inner dead center, and the instead of bottom dead center, we will call it as an outer dead center. Okay, that's it. So, in this PV diagram again, one is the uh, outer dead center or the bottom dead center, and 2 represents the inner dead center or the top dead center. So the volume V2 is the clearance volume, okay, and volume V1, that is from origin to the state point 1. V1 represents the total volume, and the swept volume is V1 minus V2, because piston will be sweeping between 1 and 2. Okay, sweeping between 1 and 2. Swept volume is V1 minus V2. Now in the question it is given that if the clearance volume is 20% of the swept volume, so clearance volume is V2, V2 is 20% of swept volume. Swept volume is V1 minus V2. Okay, so I hope this is clear. Clearance volume V2 is 20% of swept volume. Swept volume is V1 minus V2. Okay, so I have given this picture for you to understand about the clearance volume and swept volume. Okay, because this represents the clearance volume here. Now piston is at top dead center, that is at state point 2 over here. Okay, so the volume remaining between the top and the state point 2, this is clearance volume as shown over here. This is clearance volume. Okay, and the piston will be sweeping between these two centers, top dead center and bottom center, that is V1 and V2. So this will be the swept volume between V1 and V2, and the total volume is the sum of swept volume and clearance volume. Okay, now moving on from this expression, that is V2 is equal to 0.2 20 times V1 minus V2, we have arrived at a relationship for V1 and V2. So V1 by V2 is equal to 6. Now V1 by V2 is the V1 is the total volume, and V2 is the clearance volume, right? V1 by V2, total volume by clearance volume, represents compression ratio R. So the compression ratio R is 6. Okay. Now going to the adiabatic process 1 to 2, we need to find out the temperature at the end of the compression. Okay, we need to find out temperature at the end of compression. So at the end of compression means from 1 is the start of compression and 2 is the end of the compression. So we need to find out T2. Okay, so to find, we need to find T2, and then we need to find the air standard efficiency of the cycle eta. Fine. So in order to find T2, 1 to 2 is a reversible adiabatic process. So for an adiabatic process, we can write the relationship between temperature and volume, which we already know. Okay, for adiabatic process, relationship between temperature and volume is T2 by T1 is equal to V1 by V2 raised to gamma minus 1. Okay, T2 by T1 is equal to V1 by V2 raised to gamma minus 1. From this, T2 is equal to T1 into V1 by V2 raised to gamma minus 1. Now V1 by V2 is the ratio of total volume by clearance volume, that is compression ratio R. Now we have already found an expression for compression ratio R using the equation for clearance volume and swept volume. From this we got a relationship for compression ratio R, which is 6. So from this you can find out T2. T2 is equal to 614.30 Kelvin. 614.30 Kelvin. So that is temperature at the end of compression T2. Now we need to find out the efficiency of the cycle. Now efficiency of the cycle, you already know the expression is 1 minus 1 by r raised to gamma minus 1. 1 minus 1 by r raised to gamma minus 1. You know r is compression ratio 6. Gamma is actually not given in the question. But since it is an air standard cycle, the working fluid is air. So for air, the value of gamma is 1.4. You can take gamma as 1.4. So 1 minus 1 by 6, compression ratio R is to gamma minus 1. Compression ratio R is 6 and gamma is 1.4. So 1.4 minus 1. So you'll get the efficiency as 51.16 percentage, 0.5116. That is 51.16 percentage is the efficiency of this particular Otto cycle. Okay. So I hope the problem is clear. Okay. So now we'll proceed to diesel cycle. Okay. Now diesel cycle was invented by Rudolf Diesel, and the diesel engines or compression ignition engines, that is CI engines, works based on this cycle. Okay. The Otto cycle which we have seen earlier was a spark ignition engine. Okay, it was an SI engine. You can see a spark ignition engine because we provide a spark for the combustion process. Okay? We provide a spark for the air and fuel to burn. That is why it is an SI engine, and it was a constant volume cycle. Heat addition was happening at constant volume. Okay. Now we will be discussing about diesel cycle, which is a compression ignition engine. That is here the burning happens due to compression that is happening inside the piston cylinder. Okay, inside the cylinder a compression is happening, and due to the heat of the compression the fuel burns. That is why it is known as a CI, compression ignition engine. So this engine will not have a spark plug. It will be using the heat of compression to burn the fuel. And here the heat addition is happening at constant pressure. Process 2 to 3 is the heat addition process, which is happening at constant pressure, due to which it is known as a constant pressure cycle. Okay, this cycle is also known as a constant pressure cycle. Our diesel engines works based on this cycle. Now we will see the cycle in detail. Let us look into the PV, pressure, volume, and TS, temperature, entropy diagram. First, the pressure volume diagram. So here also we have 4 processes. First one is a reversible adiabatic compression, 1 to 2. Okay, process 1 to 2 represents a reversible adiabatic compression process, where you can see the pressure is increasing and volume is decreasing from 1 to 2. Okay, so it is a reversible adiabatic compression. And 2 to 3 is a constant pressure process. It is a horizontal line on the PV diagram. It is a constant pressure process where heat is added, Q amount of heat is added. 3 to 4 is a reversible adiabatic expansion process where the pressure is decreasing and volume is increasing. And 4 to 1 is a constant volume. It is a vertical line on PV diagram. It is a constant volume heat rejection process. Okay. So since heat addition is at constant pressure, the cycle is known as a constant pressure cycle. Okay. So please remember, in diesel cycle, heat addition is at constant pressure and heat rejection is at constant volume. Whereas in Otto cycle, both heat addition and heat rejection was at constant volume. Okay. Now the same cycle has been represented on TS diagram, temperature entropy diagram, where you can see 1 to 2 is a vertical line because it is a reversible adiabatic compression. Reversible adiabatic is also known as isentropic process. Okay, and here the temperature increases from state point 1 to 2. Now 2 to 3 is a constant pressure heat addition process. This is a constant pressure heat addition process, and the temperature has raised to state point 3. That is the highest temperature of the cycle. 3 to 4 is again a vertical line because it is reversible adiabatic, which is isentropic expansion process. 3 to 4, where temperature has decreased to state point 4. And 4 to 1 is a constant volume heat rejection process. Constant volume heat rejection process where temperature has decreased to temperature T1. Now please remember, 2 to 3 is a constant pressure process and 4 to 1 is a constant volume process. So the curves are different. Okay, these two curves are different. They are not of the same slope. These two curves have different slopes. Okay, so please note that because these two are different processes. So I hope the PV and TS diagram is clear. Now we will move on to the analysis of the cycle. As you know, if we have an engine working based on diesel cycle, which is receiving an amount of heat Q in from a higher temperature source and rejecting an amount of heat Q out to a low temperature sink, then the efficiency of the cycle can be written as air standard efficiency is equal to 1 minus heat rejected by heat supplied. Okay, 1 minus heat rejected by heat supplied. So we need to find out the heat rejected and heat supplied during these processes. Since heat is supplied during constant pressure, the heat supplied during constant pressure is given as mCp delta T, where m is mass of the working fluid, Cp is specific heat at constant pressure, and delta T is the temperature difference, that is in this case T3 minus T2. And heat rejected during constant volume processes mCv T4 minus T1, where Cv is the specific heat at constant volume. So substituting the same in the expression for efficiency, we get 1 minus mCv T4 minus T1 by mCp T3 minus T2. M is common, you can cancel out. Now Cv and Cp is there. We know that Cp by Cv is gamma, right? I have already told you Cp by Cv is gamma and Cp minus Cv is R. Okay, Cp minus Cv is R and Cp by Cv is gamma. So instead of this Cp by Cv, Cp by Cv is gamma, but here it is Cv by Cp, so you can write it as 1 by gamma, right? So instead of Cv by Cp, I have written it as 1 by gamma because Cp by Cv is gamma. So 1 minus 1 by gamma, gamma is the index of adiabatic expansion, into T4 minus T1 by T3 minus T2. Okay, now that is the temperatures at state points 1, 2 and 3. So this is the expression for standard efficiency of diesel cycle, and you can use this expression if you know temperatures at all salient points. Now going for a shortening of this equation. So we can see V3 by V2. Okay, let us take the case of V3 by V2. We have 3 here and state point 2 here. So V3 by V2, that ratio, that volume ratio is known as cutoff ratio. Okay, the ratio V3 by V2, volume ratio is known as cutoff ratio. Cutoff ratio represented as rho. Cutoff ratio represented as rho. Okay, so the heat addition stops at state point 3. Here starts at state point 2. So that ratio, that volume ratio is known as cutoff ratio rho. Next is V4 by V3. This is state point 4, V4 by V3. Okay, this is the expansion process. This is the expansion process from 3 to 4. So V4 by V3 is the expansion ratio. V4 by V3 is expansion ratio represented by R1. And V1 by V2. V1 is the total volume and V2 is the clearance volume. So V1 by V2 is the compression ratio R, right? Compression ratio R, that we know. V1 by V2 is compression ratio R. So in this case, we have 3 ratios. One is cutoff ratio. Cutoff ratio is the ratio between V3 and V2. So V3 is where heat addition stops and V2 is where heat addition starts. V3 by V2 is cutoff ratio rho. V4 by V3. V4 is where expansion stops and V3 is where expansion starts. V4 by V3 is known as expansion ratio R1. And V1 by V2. V1 is the total volume and V2 is the clearance volume. So V1 by V2 is the compression ratio R. Now, the relation between these two ratios, we need to find out the relation between all these ratios. So here, V4 by V3. Okay, let us take where V4 by V3. V4 by V3 is equal to V4 by V2, this is V4 and this is V2, V4 by V2 into V2 by V3, okay, into V2 by V3. Now this is correct because if you cancel these two V2s, it will be V4 by V3, okay. So we have added a V2 in the numerator and denominator, so this is okay. Now what is V4 by V2? V4 is actually equal to V1, so instead of V4 you can write V1. So that is V1 by V2. Now V1 by V2, we already know V1 by V2 is total volume by clearance volume, that is compression ratio R. And V2 by V3. V2 by V3. We know V3 by V2 is rho. V3 by V2 is rho. So you can write this as 1 by rho. Okay, you can write this as 1 by rho. And V4 by V3, V4 by V3 is expansion ratio, that is R1. So R1 is equal to R into 1 by rho. Okay. So R1 is equal to R by rho. R1 is expansion ratio, R is compression ratio, and rho is cutoff ratio. So we got R1 is equal to R by rho. This is the relationship between these 3 constants. Okay, R1 is equal to R by rho. Next, moving on to the different processes that are happening in the cycle. Process 1 to 2. Process 1 to 2 is a reversible adiabatic conversion process. So for reversible adiabatic process, you can write the relationship between temperature and volume. T2 by T1 is equal to V1 by V2 raised to gamma minus 1. or T2 is equal to T1 into V1 by V2 raised to gamma minus 1. V1 by V2 is total volume by clearance volume, that is compression ratio R. So T2 is equal to T1 into R raised to gamma minus 1. Now for constant pressure process 2 to 3, okay, constant pressure process 2 to 3. Actually, this is a ideal case, right? So P1 V1 by T1 is equal to P2 V2 by T2. Now, since pressure is constant, you can cancel pressure. So pressure won't be there, and you can write the relationship between temperature and volume, right? This is actually, this expression is actually P3 T3 by V3 is equal to P2 T2 by V2, but pressure is same at 2 and 3. So you can cancel that pressure and you will get T3 by T2 is equal to V3 by V2. V3 by V2, you know it is the cutoff ratio rho. So T3 is equal to T2 into rho. T3 is equal to T2 into rho. Okay. Now T3 is equal to, since it is T2 into rho, T2 we already know T2 is T1 into R raised to gamma minus 1. Substituting that here, T3 is equal to T1 into R raised to gamma minus 1 into rho. Now for adiabatic process 3 to 4, you take 3 to 4, this is reversible adiabatic expansion. You can write the relationship between temperature and volume. T3 by T4 is equal to V4 by V3 raised to gamma minus 1. V4 by V3 is the expansion ratio R1 raised to gamma minus 1. Okay, R1 raised to gamma minus 1. Now R1, you already know what R1 is. Okay, we have derived an expression for R1 previously. R1 is R by rho. Okay, so substituting that here, we have R by rho raised to gamma minus 1. Right, that is R raised to gamma minus 1 by rho raised to gamma minus 1. So we have T3. Okay, this is T3 by T4 is equal to R1 raised to gamma minus 1. Now we need T4. Okay, we need expression in terms of T4. So T4 is equal to T3 by R1 raised to gamma minus 1. Right, T4 is equal to T3 by R1 raised to gamma minus 1. So this will be the reciprocal. Since it is 1 by R, we have written it as T4 is equal to T3 into rho raised to gamma minus 1 by R raised to gamma minus 1. Right. Maybe I'll say it once again. From this expression, we have T3 by T4 is equal to R1 raised to gamma minus 1. But we need the expression in terms of T4. So T4 is equal to T3 by R1 raised to gamma minus 1. T3 by R1 raised to gamma minus 1. Okay. Now we know that R1 is equal to R raised to gamma minus 1 by rho raised to gamma minus 1. So instead of 1 by R1, we are writing the reciprocal of this term. So T3 into rho raised to gamma minus 1 by R raised to gamma minus 1. So we got T4 is equal to T3 into rho raised to gamma minus 1 by R raised to gamma minus 1. Now instead of this T3, we have T3, an expression for T3 here. You can substitute that here. Okay, when you substitute that, there is an R raised to gamma minus 1, here an R raised to gamma minus 1 which will cancel out. And there is a rho, and here is a rho raised to gamma minus 1. So we'll get rho raised to gamma, and you'll get T1. So T4 is equal to T1 into rho raised to gamma minus 1. Now see, what have we done here? We have converted, here we have converted T2 in terms of T1, here T3 in terms of T1, and here T4 in terms of T1. So now we have all temperatures T2, T3 and T4 in terms of T1. Substituting this in the expression that we have derived here, efficiency is equal to 1 minus 1 by gamma into T4 minus T1 by T3 minus T2. Here we know T2, T3 and T4 in terms of T1. So substituting in that expression, we'll get 1 minus 1 by gamma into, instead of T4, here we have T4, instead of T4 it is T1 into rho raised to gamma. So T1 into rho raised to gamma minus T1 by, instead of T3, we have here T1 into R raised to gamma minus 1. So T1 into R raised to gamma minus into rho minus. Instead of T2, it is T1 into R raised to gamma minus 1. So here, I think R raised to gamma minus 1 is a common term. So that can be taken outwards. Okay, so 1 minus 1 by gamma into 1 by R raised to gamma minus 1. That is a common term. And T1 is common all. So T1 will cancel out. So on the numerator, we have rho raised to gamma minus 1. By here it is rho minus 1. Okay, rho minus 1. So this is the expression for isolated efficiency of a diesel cycle. Efficiency is 1 minus 1 by R raised to gamma minus 1 into 1 by gamma into rho raised to gamma minus 1 by rho minus 1, where R is the compression ratio, that is the ratio of total volume by clearance volume. Gamma is the index of adiabatic expansion, and rho is cutoff ratio, that is the ratio of V3 by V2. Okay, rho is cutoff ratio, V3 by V2. So this is the expression for efficiency of a diesel cycle. So I hope the analysis of diesel cycle is clear. Please go through the derivation. Okay. So next we'll move on to a numerical on diesel cycle. Okay. So an ideal diesel cycle operates on 1 kilogram of air with an initial pressure of 1 bar and a temperature of 35 degrees Celsius. The pressure at the end of the compression is 33 bar and cut off 6% of the stroke. Determine the compression ratio and heat supplied, heat rejected, and thermal efficiency of the engine. Okay. So in order to solve the problem, first identify the cycle. So the cycle is a diesel cycle. Given the question, you can draw the diesel cycle on PV and TS diagram. Okay. And mass of air is 1 kilogram. Then we will see the after drawing the PV and TS diagram, we will see the given quantities. So mass of air is given as 1 kilogram with an initial pressure of 1 bar and temperature of 35 degrees Celsius. So initial pressure and temperature, if you take the diagram for Otto cycle, the initial conditions are given. State point 1, initial pressure and temperature, okay, at this point is given. Okay, so the initial pressure and temperature is given as temperature T1 is 27 degrees Celsius. Sorry, the initial pressure is given as 1 bar. So pressure P1 is equal to 1 into 10 raised to 5 Newton per meter square. Initial temperature T1 of 35 degrees Celsius plus 273, that is 308 Kelvin. Okay. The pressure at the end of the compression is 33 bar. At the end of the compression, so 1 to 2 is the compression process. At the end of the compression is state point 2. So pressure P2 is 33 bar, that is 33 into 10 raised to 5 Newton per meter square. And the cutoff is given as 6% of stroke. Okay. Cutoff ratio is the ratio of V3 by V2. Okay. It is given as 6% of the stroke volume. Fine. Now we need to find out the compression ratio R, heat supplied, heat rejected, and thermal efficiency. So initially taking the reversible adiabatic process 1 to 2, okay, for the process 1 to 2, that is reversible adiabatic compression process 1 to 2, where the pressure, we have written the relationship between pressure and volume. Okay. So this is the relationship between pressure and volume, that is PV raised to gamma equal to constant. So V1 by V2 is equal to P2 by P1 raised to 1 by gamma. Here V1 by V2 is equal to P2 by P1. Now what is P2 and what is P1? P2 is 33 bar given in the question and P1 is 1 bar. So from this and gamma, since gamma is not given in the questions, I can take air is given as the working fluid. So for air, gamma is 1.4. Substituting 1.4, you will get V1 by V2 is equal to 12.15. What is V1 by V2? V1 is total volume and V2 is clearance volume. So V1 by V2 is compression ratio R. R is equal to 12.15. So we have found out the compression ratio R. Okay, compression ratio R. We have found out 12.15. Now again applying the temperature pressure relationship. Okay, temperature pressure relationship for reversible adiabatic process 1 to 2. Temperature pressure relationship is given by T2 by T1 is equal to P2 by P1 raised to gamma minus 1 by gamma. T2 by T1 is equal to P2 by P1 raised to gamma minus 1 by gamma. From this, T2 is equal to T1 into P2 by P1 raised to gamma minus 1 by gamma. You know T1, temperature T1 is given in the question as 308 Kelvin. P2 by P1 pressure ratio is also known. You can find out temperature T2. So temperature T2 is equal to 836.4 Kelvin. Okay. Now we will be applying the expression of cutoff ratio and subto volume, because here cutoff is 6% of stroke volume. Okay, cutoff is 6% of stroke volume. Here we have written V3 is equal to V2 plus 0.06 into V1 minus V2. Now 0.06 into V1 minus V2. V1 minus V2. What is V1 minus V2? V1 is the total volume and V2 is clearance volume. So clearance volume minus, the total volume minus clearance volume will give you the subto volume. Okay. So this is the subto volume and we are taking 6% of the subto volume. Okay. 6% of the subto volume is equal to, you take this V2 outside, you will get V1, V3 minus V2, right? So 6% of the subto volume, 6% of subto volume is equal to V3 minus V2. V3 minus V2 is the cutoff. Okay, because V3 is the volume at which the heat addition ends, and V2 is the volume at which heat addition starts. So V3 minus V2 is the cutoff. Cutoff is equal to 6% of swept volume. Okay, 6% of swept volume. So V3, from that we have V3 is equal to V2 plus 0.006 into V1 minus V2. And so here I think okay, V3 is equal to V2 plus 0.006 into V1 by V2. We know the ratio of V1 by V2. So you can substitute V1 in terms of V2. V2 is 12.15. V1 is 12.15 V2. Substituting that over here, we'll get V3 in terms of V2. Okay, V3 is equal to 1.669 V2. So we get the ratio of V3 by V2. V3 by V2, that ratio is known as cutoff ratio. Okay, V3 by V2 is known as cutoff ratio rho, which is equal to 1.669. So there is a difference between cutoff ratio and cutoff. Okay, so cutoff ratio is the ratio of V3 by V2, and cutoff is V3 minus V2. Similarly, this is swept volume V1 minus V2. So we get cutoff ratio rho as 1.669. Okay, next moving on to the constant pressure process 2 to 3. So 1 to 2 was reversible adiabatic compression, and 2 to 3 was constant pressure heat addition process. So for the constant pressure process, we are writing the relationship between pressure, volume and temperature. That is P2 V2 by T2 is equal to P3 V3 by T3. But since pressure is constant, we have V2 by T2 is equal to V3 by T3. From this, you have T3 by T2 is equal to V3 by V2. V3 by V2 is the cutoff ratio, which we already know, and we know the temperature T2. Okay, we have found out T2 is 836.4 Kelvin. So you will get the temperature T3. Now this temperature T3 is the highest temperature of the cycle. Okay, T3 will be the highest temperature of the cycle, that is 1395.95 Kelvin. Next is you have to find out the heat supply. Now heat supply is happening during the process 2 to 3, right? It is the constant pressure heat addition process. So the expression for constant pressure heat addition is MCP delta T, MCP into T3 minus T2. M, mass of air, is given as 1 in the question. Cp for air is 1.005 kilojoule per kilogram Kelvin. That you have to remember, it is a standard value. Cp of air is 1.005 kilojoule per kilogram Kelvin into T3 minus T2, that is a temperature difference. T3 we have found out, T2 also we know. So you'll get heat supplied as 562.35 kilojoules. Okay, 562.35 kilojoules. Cp value of air, you should remember, it is a standard value 1.005 kilojoule per kilogram Kelvin. Next is the expression for efficiency. So air standard efficiency of diesel cycle is given by 1 minus 1 by R raised to gamma minus 1 into rho raised to gamma minus 1 by rho minus 1, where R is compression ratio, which we have already found out. Gamma for air is 1.4. Rho is cutoff ratio, we have found out that also. So substituting, you will get efficiency as 58.77%. Now we already know that for a engine that is working between a high temperature source and a sink, the efficiency is given as 1 minus heat rejected by heat supplied. So efficiency is 58.77, that is 0.5877 is equal to 1 minus heat rejected by heat supplied. Heat supplied we already know. From this you can find out heat rejected to be 1 minus, okay, heat rejected is 231.86 kilojoules. Okay, 231.86 kilojoules. Alternatively, you can also find out heat rejected by using the expression MCV, because heat rejected is a constant volume, and the process is from, if you take the diesel cycle, the process of heat rejection is happening from 4 to 1. So if you know T4 and T1, if you know the temperatures T4 and T1, we can use the expression MCV T4 minus T1. Okay, MCV T4 minus T1, where CV is specifically constant volume. For air, it is 0.718 kilojoule per kilogram Kelvin. Okay, CV of air is 0.718 kilojoule per kilogram Kelvin. So that is an alternate method. If you know the temperatures T4 and T1, you can use that equation to find out heat rejected. So I hope this problem is clear. Please go through more problems on Otto and Diesel cycle. Okay. Okay. So I hope we have discussed regarding both Otto and Diesel cycle, its cycle analysis as well as sample problems. Now practice the derivations and practice more problems. Okay, so that it will be clear to you. So more practicing more problems will help you to be thorough uh, thorough with this. Okay. So with this, I'll stop the presentation.